ഹലോ. ആ മാം, റിസോഴ്സ് പേഴ്സൺ വരാൻ ഒരു 5 മിനിറ്റിൻ്റെ ഒരു ചെറിയൊരു ലാഗ് ഉണ്ട്, അത് കഴിയാം. ഹലോ. ആ മാം, ഹലോ, റിസോഴ്സ് പേഴ്സൺ വരാൻ ഒരു 5 മിനിറ്റിൻ്റെ ഒരു ചെറിയൊരു ലാഗ് ഉണ്ട്, അത് കഴിയാം. ഹലോ മാം, മെയിലിൽ ചെയ്തിട്ടുണ്ടോ? ഹലോ മാം, സ്റ്റാർട്ട് ചെയ്യാം. ഹലോ മാം, മാം ഒന്ന് അൺമ്യൂട്ട് ചെയ്യോ? മാമിൻ്റെത് ഇപ്പം മ്യൂട്ട് മോഡിലാണ് നിൽക്കുന്നത്.
ഹലോ.
ഓക്കെ, ഓഡിബിൾ ആണ്. ഇപ്പോൾ ഓഡിബിൾ ആണ് മാം. ഓക്കെ. ഓക്കെ, എന്നാൽ ഫോർമൽ സെഷൻ സ്റ്റാർട്ട് ചെയ്തോട്ടെ?
ചെയ്തോളൂ.
ഓക്കെ, ശരി മാം, താങ്ക് യു.
Okay. Good morning to all. It's my pleasure to be a moderator for this webinar. I am Susmita Bose, and on behalf of welcome to all of you to Haufi, the celebration of Space Week, which is conducted by the Department of Physics, St.Thomas College, Ranni, as a part of International Space Day celebration. With the grace of God, we are about to begin this program. We appreciate you for taking your time to join us today. We hope you will learn a lot today. We have lined up for you to be fruitful and engaging. So, to begin with, I welcome our dearest teacher and head of physics department, Professor Anju Joseph, for the welcome speech.
A warm greetings to all. Respected Principal, Dr. Eliama Kurula, our resource person, Dr. K. Indulega, our program coordinator, Ms. Rivalsa K., all other faculties and students. Today, Department of Physics, St.Thomas College, Ranni, is hosting a webinar as part of International Space Week celebration. The topic of the webinar is Black Holes at Work. As part of Space Week celebration, we are arranging a series of programs. The first one was a sky watching session conducted last week. The webinar is the second one, and third one is the intercollegiate quiz competition on 22nd. In this occasion, I would like to thank the students who took initiative in organizing a program in connection with the Space Week celebration. The students, along with our program coordinator, Ms. Rivalsa K., did all the arrangements of the program. The space study is the topic of fascination at all times. The Space Week is celebrating every year to commemorate two milestones in space exploration. One is 4th October, marking the launch of the first man-made satellite Sputnik 1 in 1957, and the other on 10th October 1967, marking the day on which the UN Declaration for Peaceful Uses of Outer Space. This year's theme of Space Week celebration is Satellites Improve Life. That is, satellites and their broad benefit, the theme of this year's Space Week celebration. Let me move on to my duty. Our principal, Dr. Eliama Kurula, has joined with us. Teacher is giving constant encouragement and support in organizing various programs and constantly working hard for the progress of our college. I extend a hearty welcome to you, ma'am.
Thank you.
Our today's resource person is Dr. K. Indulega, Professor, School of Pure and Applied Physics, MG University, Kottayam. Teacher is doing cutting-edge research in astrophysics. She is having collaborations with the Raman Research Institute and the Inter-University Center for Astronomy and Astrophysics. Teachers' work led to the development of so many internationally useful software packages. We are really proud to have such an eminent personality like Indulega teacher as our resource person. With extreme pleasure and honor, I welcome you, ma'am. I welcome all the participants of this webinar. Hope this session will be fruitful to one and all present here. Thank you.
Thank you, ma'am. Now, I welcome our dearest principal, Dr. Eliama Kuruvula, for the presidential address.
Good morning to one and all. Our distinguished Chief Guest, Dr. Lindilekha K., School of Pure and Applied Physics, MG University, Kottayam, Head of the Department of Physics, Assistant Professor Anju Joseph, Coordinator, Assistant Professor Srivalsa, Professors of the Physics Department, Student Coordinator Aromal, colleagues, dear students, and all the participants. Black holes were considered as a region of space from which nothing can escape. A black hole is a place in space where gravity pulls so much that even light cannot get out. The gravity is so strong because matter has been squeezed into a tiny space. This can happen when a star is dying. Because no light can get out, people can't see black hole. They are invisible. Space telescopes with the special tools can help find black holes. NASA is using satellites and telescopes that are traveling in space to learn more about black holes. This spacecraft helps scientists answer questions about the universe. Black holes can be big or small. Scientists think the smallest black holes are as small as just one atom. Different kinds of black holes are identified by scientists, such as stellar, supermassive, etc. Scientists have found proof that every large galaxy contains a supermassive black hole at its center. Scientists think the smallest black hole formed when the universe began. A black hole cannot be seen because strong gravity pulls all of the light into the middle of the black hole. But scientists can see how the strong gravity affects the stars and gas around the black hole. Scientists can study stars to find out if they are flying around or orbiting a black hole. When a black hole and a star are close together, the high energy light is made. This kind of light cannot be seen with human eyes. Scientists use satellites and telescopes in space to see high energy light. Black holes do not go around in space, eating stars, moons, and planets. Earth will not fall into a black hole because no black hole is close enough to the solar system for Earth to do that. Scientists think supermassive black holes were made at the same time as the galaxy they are in. When a black hole and a star are close together, high energy light is made. This kind of light cannot be seen with human eyes. It is now shown that by Stephen Hawking that the matter inside a black hole is not completely isolated from the rest of the universe, and that given a sufficient length of time, black hole will gradually dissolve by radiating away the energy of the matter that they contain. The first rule for anyone dealing with a black hole is that don't get too close. Do so are in a one-way trip because there is no coming back once you fall into a black. Let it be a useful day for all the participants. Best wishes for the webinar and thank you.
Thank you, ma'am. Today, we'll be having a technical session on the topic Black Holes at Work, handled by our eminent guest, Professor Indulekha K. from School of Pure and Applied Physics, MG University, Kottayam. I welcome our program coordinator, Ms. Srivalsa K. to introduce our guest to you.
Good morning. I'm very pleased to welcome Professor Dr. K. Indulekha for our special event, Haufi 2020. Professor K. Indulekha is a well-known personality in the field of astronomy and astrophysics. Currently, she is a professor in School of Pure and Applied Physics, MG University, Kottayam. She did her master's in theoretical physics from Kerala University and PhD from IISc Bangalore. Her area of interest are galaxies and stellar cluster. Dr. Indulekha is a member of board of many nationally and internationally reputed journals and various associations. Hello, ma'am. Screen share നമ്മൾ ചെയ്യണോ presentation?
അടുത്ത slide. I can't see.
Okay, ma'am.
Visible to you?
No, ma'am.
No.
Okay, 1 second, ma'am. ഒരു 1 minute ഇപ്പോൾ പ്രസന്റ് ചെയ്യാം. പ്രസന്റേഷൻ മാം മെയിൽ ചെയ്തിട്ടുണ്ടോ?
ടീച്ചറിന്റെ മെയിൽ ഐ ഡിയിലേക്ക് അയച്ചിട്ടുണ്ട്, യാഹൂ മെയിൽ.
ഹലോ മാം, നമ്മൾ പ്രസന്റ് ചെയ്യട്ടെ എന്നാല്?
വിൻഡോ മാറ്റിയാൽ മതി. ക്ലിക്ക് ചെയ്താൽ മതി, ഫുൾ സ്ക്രീനിലേക്ക് മാറും. സൈഡിലുള്ളത് ചെറിയ ട്രയാങ്കിള്, നടുക്കുള്ള ട്രയാങ്കിള്. അതെ. ഐ തിങ്ക് കൺട്രോൾ എല്ലും കൂടെ വേണമെന്ന് തോന്നുന്നു. കൺട്രോൾ എൽ. വിൻഡോ മാറിപ്പോയി. കൺട്രോൾ എൽ കൊടുക്കാം. കൺട്രോൾ എൽ. ഹലോ,
മാം ഓക്കെ അല്ലേ?
അതെ. Can you hear me?
Yeah.
Welcome. Welcome. Okay. Then maybe I will start.
Okay.
So first, I thank the principal, head of the department, and the coordinator of this Space Week celebration for inviting me to give this talk. I've given the title as Black Holes at Work. Now, this, uh, as you notice, I have an X-ray astronomer who was giving it. So, why I have given the title as Black, simply look at black holes as just sitting there, but that work, and hopefully across the next few question, black holes, they don't allow even light to escape from them. Then how do you expect to see them? We'll see that black holes are at work, and because of that, they certain phenomena happen which produces. Everybody understands Malayalam?
Ma'am, we have participants outside Kerala.
Processes that produce a lot of light, we recognize. So here it is, gravity at work. Everybody who has ever written, extremely easy. Life is easy once you are on a downslope. Gravity will do all the work and you can simply sit and enjoy the ride. So this is a picture of gravity at work. Next slide, please. Now, if learn that the gravitational field is what is called a conservative force field. In that, energy is conserved. If other dissipative processes are not acting, the total energy of a body will be a constant in its movements and through a gravitational field. So I've written the equations here. So kinetic energy plus potential energy equal to constant. And that can be shown for the gravitational field in the following fashion. This particular force is one of the kinds which can be written in terms of the gradient of a scalar field. Remember, force is a vector field. Gravitational force field is a vector field. Forces are vectors. So if you write F equal to minus grad phi, then if you think of one-dimensional motion, just to simplify the mathematics, those who are interested in the full F equal to minus grad phi formulation can look it up in Google or textbooks like Goldstein's Classical Mechanics and study this. So if you write F equal to minus d phi by dx, and then by Newton's equation you have that is equal to m into a, that is m d square x by dt square in one dimensions. So you multiply with dx by dt and integrate over dt, you will get minus phi plus phi 0 equal to half m square, or half m square plus phi equal to phi 0. So phi 0 is a constant, so kinetic energy plus potential energy equal to constant is what you get. If you look at so next what I have in the next slide please. What I have given is something called the virial theorem, which again starting from Newton's law of motion we can get. So it can be shown even for dissipative forces, but we are not, the virial theorem can be proved even for dissipative forces in slightly changed form it will be. But here we are showing it for this particular conservative force field. To write F equal to minus d phi by dx equal to mx double dot, but the dot denotes differentiation with respect to time. Then you will get f dot x equal to minus d phi. I think it should have been f dot dx. That is equal to minus d phi. There is some slight mistake. I always need to write out when you take f dot x, that will be minus d phi by dx only, dot x. is equal to, there's a mistake in those equations. So you write f dot x is equal to minus d phi by dx dot x equal to mx double dot x. Mx double dot x in this fashion. You take x square and take its second derivative with respect to time. Now you will find that if you take d square of by dt square of x square, you will get a term x double dot x as well as an x dot square term. So the term mx double dot x we can write in terms of d square of x square by dt squared and minus x dot square. So you insert that into the f dot x equal to minus d phi by dx dot x equal to mx double dot x equation. You'll be able to write f dot x as equal to half d square by dt square of mx square minus mx dot square, which is what is written there. Now, if you take the gravitational force and look at f dot x, we find that it can be written in terms of the total potential energy of the system. So we will get from Newton's equation, we will be able to work out the following expression, which is called the dynamic Virial theorem, that half of d square by dt square of mx square is equal to twice kinetic energy plus potential energy, because mx dot square is twice the kinetic energy. Now, what is the significance of this Virial theorem, which you will study in classical mechanics? It appears in Goldstein, for example. Time and take time average square by dt squared integrated over a long time. Then what will happen is the integral of d square of mx square by dt square will be can be arbitrarily large depending on the time interval over which you are. So
ഹലോ
for large
മാം
yeah.
ഇടയ്ക്ക് ഓഡിയോ കട്ട് ആവുന്നുണ്ട്.
So what to do? I don't know.
മാം മേ ബി വീഡിയോ ഓഫ് ചെയ്ത് കഴിഞ്ഞാൽ കുറച്ചും കൂടി ഓഡിയോക്ക് ക്ലാരിറ്റി കിട്ടാൻ മതിയാവും.
എന്തോ
വീഡിയോ മാമിന്റെ വീഡിയോ ഓഫ് ചെയ്ത് കഴിഞ്ഞാൽ ഓഡിയോക്ക് ചിലപ്പോൾ ക്ലാരിറ്റി കിട്ടാൻ മതി.
I'll do that. Me?
Yes, yes ma'am, കേൾക്കുന്നുണ്ട്. Yes ma'am.
Okay, fine. So this gives us what is called the, for example, you will not get, if it is a bound system like system or the hydrogen atom, for example, the separations, the particle separations will not become large. So square of x square over long time scales will be equal to 0, and you get the famous Virial theorem that twice kinetic energy plus potential energy equal to 0 for a system in equilibrium. You can example the orbits of planets around the sun or the hydrogen atom and verify for yourself that the Virial theorem actually holds. Now, suppose you consider what is called the quasi, that is, a system is changing but very slowly with respect to time. In that case, its dimensions are changing very, very slowly with respect to time, in which case you can write twice kinetic energy plus potential energy. So one way that twice its kinetic energy plus its potential energy taken in, it looked at in a slightly different fashion. It tells you that the twice slide with respect to gravitational fields not spherically symmetric. They're spherically symmetric. You can treat the external gravitational field of those symmetric field, but if the objects are not spherically symmetric, you can see that if you look at any one of these objects, one will be is closer to the other body than the other end. And gravitational force is proportional, inversely proportional to the square of the distance. So the end of the ellipse that is close, which is farther from the. So because of this gradient of the respect to distance, spatial gradient, what will happen is these kind of objects which are not spherically symmetric. The next slide, please. The previous slide is showing still. Objects which are not spherically symmetric will set each other into rotation. You try pushing a book by its edge, you will find that the book rotates. Exactly the same sort of thing happens to bodies which are not spherical. And in the universe, you find a lot of gas, and unless it has all been drawn and held under self-gravity, objects will not in general be, gas clouds, etc., will not in general be spherical. So gas clouds in the universe set each other into rotation, and that is why you find everything rotating, planets, stars, galaxies, everything you find to be in rotation. It's because of this factor. It is called a tidal torquing. Now, another thing which you have studied, if you take Newton's equations again, I have written them on the right-hand side. You can see by those equations, if you take Newton's equation and take R cross F, which is what is called known as the torque of the force, then you will find that you can write R cross F equal to R cross dP by dt, which can be rewritten as d by dt of R cross P. You identify R cross P as L, usually called the angular momentum. Then you find that if it is the gravitational force which is being considered, you have R cross GMM by R square, R hat is in the radial direction, equal to 0 equal to d by dt of R cross P. That equation I should have written as R cross P. It is equal to dl by dt. Oh, no, sorry, that equation is correct. I am just pointing out that R cross, if gravitational force which we take here is equal to 0, as well as dr by dt cross P is equal to 0, because dr by dt is velocity, and velocity and momentum have the same direction, it is V cross P. Since dr by dt cross P is 0 is the reason why we wrote in the just previous line R cross dP by dt is equal to d by dt of R cross P. That is why we could write that. So we find that if you define L equal to R cross P, multiply numerator and denominator by R squared, you rewrite it as mR square into R cross V by R square. But R cross V by R square is the angular velocity. So you write L is equal to I omega, in exact analogy with linear momentum P is equal to mv. So we for the torque, and you find that tau equal to R cross F equal to dl by dt now can be written as, if you rewrite L as I omega, I d omega by dt plus di by I d omega by dt R into P parallel. P parallel means since we had R cross omega coming up in the definition of omega, R cross P, R cross V coming up, R cross P coming up in the definition of L, you will pick up an RP parallel into omega there. So this is an expression which tells you, connects the angular acceleration d omega by dt to this, will find an angular acceleration which is given by this expression. So the next slide, please. So bodies have been set into rotation, all because of the gravitational field. Angular momentum is conserved for a closed system. Now let us look at another feature which comes up. Magnetic fields. In astronomy, you find that the Earth has a magnetic field, Mars has a magnetic field, Sun has a magnetic field, the galaxy has a magnetic field. So how could this magnetic fields have arisen in the universe? Because if you take the Big Bang model, for example, when the universe is extremely dense, it's supposed to have started from a very dense, hot phase. At that age, period of the origin of the universe and the evolving and becoming the fields from which are present now, you know that magnetic fields are also conserved quantities as far as conducting plasmas are concerned. So the magnetic fields in the early universe should have been extremely strong to become, due to the expansion of the universe, changing in their strength, magnetic flux is concerned, changing in their strength and becoming the fields which you notice now. But if there was an extremely strong magnetic field at the early universe, the universe will not show anisotropy. That is, whichever direction you look at, it looks the same. And the relic radiation from Big Bang, the cosmic microwave background radiation, is nice and fully isotropic, except for what is called the dipole anisotropy due to the local motion of our uh, galaxy group. So you can't have magnetic fields from the beginning of the universe itself. So where did they come from? So in astrophysics, we have this what is called the Biermann battery, which is a process by which a weak seed magnetic field can be generated from a condition where there is initially zero field. So you notice the equation, the Biermann battery equation, dB by dt. This is del cross V cross B from the usual Maxwell sort of terms. In addition, if the plasma has got a grad T cross grad rho, look at the second term. If that term is non-zero, now pressure is N indicated T. So grad T means a temperature gradient and grad rho is the density gradient. If the temperature gradient and there is a temperature gradient and a density gradient which are not in the same direction, that second term
Hello. There is some network issue. Hello. Can you hear me?
Yes, Miss.
There is some network issue for our resource person, so she will join you soon. Please wait one more minute.
Hello? Hello?
Yes, ma'am. Yes, ma'am.
Yeah.
We hear you.
Continue. So we find that the second term can become non-zero if the gradient of temperature and the gradient of density are not aligned with each other, are not in the same direction. And this can happen in the early universe when if you look at the cosmic microwave background, then it provides a radiation field. And if there are rotating type of whirling motions which are there, the electron fluid will be tied more to the radiation field because of Thomson scattering, stronger process for Thomson scattering, while the proton fluid will not be as strongly coupled. So if there are rotational motions, the electron fluid will lag behind the proton fluid and potential differences can be generated, which can give rise to magnetic fields. So we have this Biermann battery process and we have the dynamo. I don't know, only old-fashioned cycles used to have dynamos where when you ride the bicycle, a potential will be generated, current can flow and the bicycle headlamp can glow. So a dynamo is a mechanism for converting flow energy, that is flow of fluid or mechanical motion, as in the case of cycle, flow energy to magnetic energy. So kinetic energy is converted to magnetic energy. Now the magnetic fields of most stars and galaxies, the Biermann battery can produce only a tiny field. This field is amplified by dynamos. So most stars, the magnetic fields of most stars and galaxies are probably sustained by dynamos. I have shown the dynamo equation there. So if you have a seed field, notice that both terms, all the terms on the right hand side of the equation involve B. So you need a starting field for dB by dt to if it becomes positive, you will have a growing field. So fields can grow by the dynamo mechanism. So we have a situation where we can have rotation, we can have magnetic fields in the universe, and both these are seen quite a lot in the universe. Now we look at this thing called hydrostatic equilibrium, which you are familiar with. If you keep a glass of water on the table, the water will be stable. Now, gravitational force is acting on the water, and you have studied by Newton's law, if a force is acting, the unbalanced force is acting, there will be acceleration to the body, matter. So here you have no one force which is acting, which is gravitational force. So this is opposed by the pressure gradient force, which you must have studied. If you have ever tried, when take in a bucket of water, if you try to push down a mug turned upside down, you find that as you go more and more under, it becomes more and more difficult to push the mug down. So you will be pushing against larger and larger pressure inside the liquid, the hydrostatic pressure. So hydrostatic equilibrium is the equilibrium of a fluid in the presence of a gravitational field. Like for example, the equilibrium of the water in the glass, or the equilibrium of our atmosphere in Earth's gravitational field, or the equilibrium of a star, which is a ball of gas under its own gravity. All these equilibria are because these pressure gradient forces are acting against the gravitational force which is present in the system. Now, in the pressure, in the case of a hot gas, it can be NKT. Like for example, in the case of atmospheric pressure, the pressure gradient in the atmosphere is opposing gravity. Now, from all these considerations, we see that hot, magnetized, rapidly rotating disks of present in all situations involving accretion in astronomy. Explain what accretion is. If you consider a gravitating object and surrounding it, gas is available, this gravitation, since it's universal, the gas can be attracted towards the gravitating, the more massive object. Now, we have studied about angular momentum. Angular momentum is r cross p. So, if you take the radial vector from this, but when will r cross p be 0? When p and r are in the same direction, that is, the gas is moving radially inward. If the gas is moving radially inward, it can fall directly onto the gravitating object. But if the gas is not moving radially inward, r cross p, the angular momentum will be non-zero. And because angular momentum has to be conserved without the action of external, if there are no external torques acting, angular momentum has to be conserved. What happens is the gas cannot fall directly onto the attracting, massive object. So what will the gas do? The gas is being attracted at a velocity which is a non-radial component to its velocity. The gas will start going round and round the object. Just like satellites or moon goes around the earth or the earth goes around the sun, etc. All this happens because they all have started with velocities which had components which were perpendicular to the radial direction from the parent body. So the gas will start going round and round. Difference because we looked at the equilibrium system, twice kinetic energy plus potential energy equal to 0. So as distance from body is heat energy of your mass. So when a gravitating body attracts gas to itself, it will fall in satisfying angular momentum conservation conditions and will slowly fall into the gravitating body, losing angular momentum during this dissipation process, because inner layers of fluid will try to accelerate the outer layers of fluid and thereby transporting angular momentum outward, and the matter can move inward. So gas disks will form in presence of gas plus attracting gravitating body. I think you have gone very much ahead in the slides. No, this is correct. So what I have shown next, the first picture is a picture taken of the M87 galaxy, which has got a supermassive black hole at the center, which you might have read about recently when the black hole at the center, a picture of it was taken by the Event Horizon Telescope. But what I have shown here, trying to emphasize here, is something else. I will come to it. The picture at the top is a picture of an accretion disk around a black hole is what has been shown because the object there is pictured as black. Now you notice something, a wispy sort of thing going upward from the black hole, like that black object at the center. Now what is this wisp-like thing? That is the question. Now we have rotation, we have angular momentum, we have magnetic fields. So as the rotating gas with embedded magnetic fields falls towards the central gravitating black hole, when the material comes close to the black hole, the magnetic field can actually penetrate the black hole. So there will be field lines penetrating the event horizon of the black hole. And you have already heard about event horizon from your teacher in the introductory speech. It is the surface, closed surface in space-time, which can trap light. It is called a closed trapped surface. So anything which goes beyond that surface, it cannot transmit information to the outside, space-time outside. But magnetic fields can penetrate that surface, and you have studied Maxwell's equations. Changing magnetic fields can produce voltages. So voltages are generated in the region. Magnetic fields can be generated. So as the incoming material and the magnetic field of the incoming material rotating the event horizon of rotating black holes, the field plus the thrown out to a jet. So that is the jet of magnetic fields and plasma is what you see as going out at the top of that picture, the top picture. Now the combination of central rotating body plus incoming rotating plasma plus magnetic fields can give rise to these kind of jets of material, plasma plus magnetic field, thrown out perpendicular to the accretion disk, that is in the direction of the angular momentum. And this jet will be a rotating jet. It is carrying away angular momentum. Now, all the things I mentioned, rotation, magnetic field, central self-gravitating object, plasma, etc. It needs a central gravitating body, that is all. Now, the first picture in the bottom row shows the jet. Look at the, oh, it is upside down, 5,000 light years long, extending from the M87 galaxy. So it is being pictured in radio as well as optical by Hubble telescope. It's 5,000 light years long. The middle picture at the bottom shows the jets which are seen in what are called binary stars, particularly X-ray binaries. So the accretion disk there is around a compact object, and your coordinator, Merikuti teacher, had actually worked on X-ray binaries. So these binary stars are systems were detected in X-rays as emitting a lot of X-rays. Now the third picture, it was taken with infrared telescopes, and you can see flux contours of infrared line radiation, that is molecular lines in the infrared, carbon monoxide line, silicon monoxide line, and the carbon sulfide line. And you can see that a central point is marked. So these are what are called bipolar outflows coming out from protostars. Stars form from gas clouds, and the gas cloud, which is unstable due to having more potential energy than kinetic energy as per the Virial equation, will collapse to extremely high density changes have to take place because these are going from densities order of 10 to the 3 hydrogen atoms per cc, just hydrogen atoms per cc, and 2, the density at the center of the sun, mean density of the sun is more like 1 gram per cc, and 1 gram can have 10 to the 23 atoms. So a difference in change in density of order 10 to the 19 or more orders of magnitude have to take place. So under these extreme collapse conditions, the system has got angular momentum. I said all gas is in rotation. So you get a rotating disk around the central collapsed object. The rotating disk has magnetic fields again. There are magnetic fields all over the universe. So all the conditions for forming the jets are satisfied, and you find in star forming clouds where new stars are forming, you do find these bipolar outflows. This just illustrates the commonality of physics in all these phenomena. See, the phenomena are so widely different, but the physics remains the same. So that is just one illustration of how you apply astrophysics to these kind of observations which you make by varied telescopes. So supermassive binary black hole is the central massive object in one case. In the other case, it's a compact white dwarf or neutron star. In the other case, it is star. And in the accretion disk, planets are later seen to form. So quite a few stars do have planetary systems due to, again, this accretion disks, such accretion disks which form during star formation, later breaking up into rings, which then can coagulate into planets. Now, one more thing I have physics I have added, it is Planck's radiation law also comes into is in operation here. We studied Wien's law, sorry, I should have written lambda max T, not lambda T max. There is a correction there. So lambda max is the wavelength of maximum emission. In the picture, you see those curves. These curves are Planckian curves for black body radiation at different temperatures. On the y-axis, you have got the power density, the amount of energy radiated per unit wavelength range per unit area of a body, etc. So you find that as the temperature decreases, the wavelength of the peak emission increases, which means the hotter a body is, the higher the frequency of the photon of maximum energy emission from the system. Now, if you look at the surface temperature of the sun, it is of the order of 5770 Kelvin. We understand that there are magnetic fields on the sun from Zeeman effect. You take spectral lines. In Zeeman effect, the two lines which are formed have opposite polarization, circular polarization. It was first detected by noticing that, if you take spectral lines, line at one edge of the line has different polarization from the other edge of the line. That was how it was first noticed when what is called the spectral resolution of telescopes were not large. Now we have better resolution, spatial resolution, and spectral resolution, and temporal resolution have all increased. You can distinguish objects which are more and more close by as separate, spectral lines which are more and more close by in wavelength as separate, and arrival of, let us say, X-ray photons, for example, occurring more and more closely in time as separate. These are the three different resolutions which we use in usual astronomical telescopes. So we have the Planckian curve. We determine the surface temperature of the sun at 5770 Kelvin. You don't expect a much X-ray emission, but once in a while you see huge X-ray flares from the sun, huge amounts of energy being radiated. These are what are called X-ray flares. And you can also have masses of plasma and magnetic field thrown out with speeds of order of, I think, hundreds up to thousands of kilometers per second. So how are these things happening in the sun? And also, if stellar temperatures are up, surface temperatures are only up to 10,000 Kelvin, you can determine it using Wien's law, for example. And you don't expect X-ray from stars in the sky. But when the first X-ray detectors were flown high, Earth's atmosphere does not allow X-rays to penetrate down to the ground too much. People are surprised to see bright X-ray sources in the sky. Scorpio X1 was one of the first ones. These were later seen to be X-rays coming out because of accretion onto compact objects like black holes and neutron stars taking place in binary systems. So these gave the first indications. X-ray astronomy gave the first indication of possibility of black holes existing in the universe, other than what was expected from theoretical considerations. Theoretical considerations most people have heard about in Einstein's theory of gravitation. You look at the spherically symmetric solution, you have Schwarzschild solution. It admits this closed, trapped surface called the event horizon, admits singularity, which you call the black hole. That is theoretical. Do they really exist in the universe was the crucial question. So SCO X1, X-ray astronomy, gave the first indications of the possibility of existence of black holes in the universe. But then how come sun is producing X-rays once in a while when its temperature is so low? We have got these flares are produced by what is called magnetic reconnection. So oppositely directed field lines coming close to each other. Plasma with oppositely directed field lines coming close to each other. A phenomenon called magnetic reconnection can take place wherein a lot of magnetic energy is dissipated as heat and kinetic energy, and the plasma is thrown in two different directions. So the plasma which is thrown outward from the sun comes out as what are called these coronal mass ejections, etc. And these can be harmful for Earth's communication systems and all if they come and push on the Earth's ionosphere and can create trouble for communication systems as well as space travelers, space stations, satellites, etc. Gravity is universal, so resisting gravity. So how do objects resist gravity? So I think we are nearing the end of this talk. So planets, they resist gravity by electrostatic repulsion of atoms which are brought too close together. The outermost electrons will repel. Stars, gas pressure plus radiation pressure will be opposing gravity. Planetary system centrifugal force. In a white dwarf stars, the degeneracy pressure of electrons are fermions. Fermions don't like sitting in the same place and same quantum number. So if you try to push them together, they will go, say, take me to a higher energy level so that I can not have the same number as everybody, quantum numbers as everybody else. So they resist being pushed together. That pressure is called a degeneracy pressure, white dwarf star. But if the mass goes beyond a certain limit, there is another peculiarity of physical systems. They love to sit in the lowest possible energy state. So fermion, the Pauli exclusion principle, if you push electrons together, the electrons will ask, put me in higher and higher and higher energy states. So that is not a good situation. So if you push them too much, they will lose the energy by combining with the protons and becoming neutrons. So beyond, if you take the mass of a body star beyond the Chandrasekhar limit, what will happen is the white dwarf star, which is supported by electron degeneracy pressure, can collapse. And the neutrons, they are also fermions. So neutron stars exist. They're supported by the degeneracy pressure of neutrons. But then people again looked at what happens if the mass of a neutron star is increased a lot, so that you try to push neutrons together a lot. So there we have the Tolman-Oppenheimer-Volkoff limit. Beyond that, we don't know anything that can oppose gravity. So you think this is such a massive star whose mass is greater than the Tolman-Oppenheimer-Volkoff limit will become a black hole. But that's proof. You've checked it from theory, that's all. On the right-hand side, I show how galaxies and are supported. The universe, it is an expanding system, total energy greater than zero. So the universe is a different issue. We are not looking at cosmology here, so I will stop with that. Now, magnetic fields and relativistic jets. So magnetic pressure is there, reconnection, solar flares, and Maxwell's equations at the event horizon give you jets. All these things I have already talked about. So we will move over this slide. This is the picture of the accretion disk. Again, the details I had talked about. On the right is that artist's impression of an accretion disk. On the left is the picture. On the right hand side is a schematic diagram of the different temperature, pressure situations that are present in accretion disk in detail, the accretion disk situation in detail. And the surrounding is from different directions. When you look, the system will appear different. If you are directly looking into the jet, you will see it in one way. If you're looking from the side, you will be seeing only the thick accretion disk, you will see something else. So the same thing can look differently, and a lot of different phenomena were unified by the theory of accretion disks. So that is what is shown on the right hand side. Now, scientists at work. Till now, we were looking at gravitation at work, producing all this radiant energy. Accretion, the friction can produce a lot of heat. So the high temperature plasma can radiate as per the Planck's law. So you have X radiation coming out because of the extreme high temperatures, etc. It's not just X radiation. If you remember the Planck curve, the higher the temperature, the higher up will be the radiation at all wavelengths. So a hotter body will emit more than a colder body of the same size at all wavelengths. So you get massive amounts of energy being put out from black holes in particular, compact objects in particular. Why? Because you saw the relation for a quasi-static equilibrium. The Virial theorem will tell you that twice kinetic energy plus potential energy equal to zero. So as the gas is flowing in, the change in potential energy will be emitted as binding energy of the gas which is flowing in, because its binding energy is changing. Now, binding energy outside, you can write it in terms of potential energy as, say, GMM by R1, R initial. And as it flows and goes closer and closer to a distance R final, let us say, the potential energy will be GMM by R final. Now, if the R smaller the value of R final, the more the amount of potential energy that will be released as binding energy. And who has the smallest known radius for a given mass? A black hole. The radius of a Schwarzschild radius of a non-rotating black hole is of the order of 2G. No, don't change the slide, please. Is of the order of, this is next one. Next one is of the order of 2 gm by c square. So since black holes are extremely compact masses, massive amounts of energy will be released as binding energy from black holes. So black holes are at work producing and releasing these huge amounts of binding energy when they pull gas into them. So scientists at work in the world of black holes is the title I have given. So in recent years, we have seen all these important discoveries, detections being made, merging black holes, releasing gravitational binding energy, not in the form of heat radiation, because both of them are black holes. There is no gas lying around. So what happens when two black holes merge? The binding energy is radiated as gravitational waves, which is what were detected in the LIGO detectors, which you saw happening in very near past. Next, I have shown this picture. We will look at that we'll see the next one. The supermassive black hole at the center of M87. That is the picture that was taken by the Event Horizon Telescope. It is accreted material releasing binding energy as electromagnetic waves. Again, black holes at work. Now, in the case of the Milky Way supermassive black hole at the center of the Milky Way, which won the one half of the Nobel Prize just announced, how were they detected? They were detected by non-Keplerian stellar orbits in a strong post-Newtonian gravitational field. I'll tell you what it means. But before that, before the discovery, which was just made about the supermassive black hole and the stellar orbits around it, what was noticed at the center of the galaxy? Powerful radio source. Now, where did this radio source, is the radio source getting its energy from? Again, bits and pieces of gas which is flowing into the supermassive black hole can produce a lot of radio radiation. And you see this central region as a powerful. Now, what did the people in the who won the Nobel? They looked at the center of the galaxy and tracked the changes in position of the various stellar objects, stars they found there over a period of 16 plus years. And the work started in 1991. So the two people who got the Nobel Prize for this, they were tracking these objects for almost the past 30 years. To work, you start in 1991, you develop the instrumentation needed, you develop the data analysis technique needed, you bring together a group of people who can work on the multiple, aspects that need multiple problems that need to be solved before you can make such complex detections. And that is how the work was done. 1991 it started, the first paper gets published 10 years later by the group. So what are non-Keplerian stellar orbits? Still now we were talking about Newtonian gravity. But when you take general relativity into account, it's not precisely Newtonian gravity when you have a spherically symmetric mass. You have to, when the effects of general relativity can be captured by approximations to general theory of relativity. By writing equations which look exactly the Newtonian fashion, F is equal to mass into acceleration, force is the gradient of a potential. Only thing is, the potential will not be simply GMM by R. You will have correction terms. These correction terms from general relativity are called the post-Newtonian terms. PPN, PN, PPN, PPN1, PPN2, etc., terms can come. So if the motion is in a Newtonian potential for a spherically symmetric object, the orbits are called Keplerian orbits. If relativistic effects, etc., are also taken into account, we call them non-Keplerian orbits. Like you must have studied that the orbit of Mercury is a precessing orbit. It is an ellipse whose major axis is keeping on rotating so that the orbit does not close also. The major axis keeps rotating. These are non-Keplerian orbits. So the black hole at the center of the Milky Way was inferred from the non-Keplerian orbits of the stars which are seen going around the object. So the shortest period object has a period of 16 years. So you have to wait at least 16 years of observations. Take it, analyze it, wait, again take, analyze, wait till you get a complete orbit. Now, tracking the motions on a photographic plate or on a picture gives you only the motions which are perpendicular to the line of sight, that is on the plane of the sky. To get the motion along this line of sight, that is the radial direction from us to the star, we use the phenomenon of Doppler effect. That is, the spectral lines will be shifted to the blue region of the spectrum, that is shorter wavelength side. If the star is approaching us, the radial velocity is towards us. And if the radial velocity is away from us, the spectral lines will be redshifted. So from the shifts, the radial component was determined. From the Doppler shifts, the radial component of velocity was determined. From the lateral shifts in the plane of pictures, you could determine the perpendicular component of velocity and thus get the total velocity. So tracking the total velocity, we can infer the orbit of the star in three-dimensional space. I will come back to this Penrose picture, which is the picture shown in this slide. We will go to the next slide. Oh, okay. So the SMBH picture we will come to slightly later. So let us complete what is, just previous slide, please. Complete what is said in the picture. This is the Penrose picture showing the formation, the closed trapped surface and the singularity. How the light cones change. That is how Penrose tracked or analyzed the formation, the singularity that occurs in the Schwarzschild or the singularity that occurs in the formation of a black hole. Instead of looking at curvature as Einstein's equations does, how do I explain curvature? Okay, suppose you take a flat sheet of paper and you draw a lot of straight lines, latitudes and longitudes on it. It will look like they intersect at 90 degrees and parallel lines will not intersect each other. Now, if you take the curved surface, which is the surface of a globe, and you draw a lot of straight lines, they will always intersect each other. Straight lines, which are shortest distance curves on a spherical surface, are what are called great circles. Circles whose center coincide with the center of the sphere. So you can see that on the spherical surface, these shortest distance paths are intersecting each other. So there is an equation, a reformulation of general theory of relativity in terms of the coming together or going apart of the paths of matter particles, which is another way of looking at curvature. You have heard about general theory of relativity, this expression, matter tells space-time how to curve and space-time tells matter how to move. So how matter moves is what is captured in what is called the Raychaudhuri equation. So the Raychaudhuri equation sort of approach was used by Penrose in analyzing the singularities, coordinate singularity and otherwise, which occurs in the formation, we expect to occur in the formation of black holes. And he proved that the proof doesn't exist in 1965. Why didn't he get a Nobel Prize? It was not experimentally confirmed. So experimentally it has been confirmed now, black holes exist. directly confirmed by the picture, and we have the one at the center of our own galaxy. So Roger Penrose got the Nobel Prize. Black holes are invisible an invisible man, we notice that there is a hat on top. In between, there is nothing, and there is a coat. So the invisible man can be inferred from whatever is clothing the invisible person. Like in the case of accretion disks cloth a black hole, and accretion disks emit a lot of light. So you infer that the invisible person, the black hole, is there. This other picture, you have see a teacup up in the air. There is a table, there is a chair, and you see a teacup moving, but there is nothing else to be seen. So objects which cannot be seen can be inferred by the action on the way they accelerate other objects. So this is the way, for example, dark matter was in. And in the case of the supermassive black hole at the center of the galaxy, the black hole is inferred from the motion of the stars which are moving around in that region. You don't see the black hole. You see stars moving around. Just like you see the cup moving, but you don't see anything else. So that is the invisible man drinking tea. So it is like the SMBH at the center of our galaxy. So in the picture at the bottom, I have shown two merging black holes. Black holes are invisible. They are sending out gravitational waves. They are waves in space-time. They are not electromagnetic radiation. Your eye cannot detect it. If they're extraordinarily strong, you will feel them as your body contracting and expanding. But they have to be incredibly strong for you to feel that. You know that the LIGO detection of gravitational waves, the displacement, the compression expansion which was there was only of the order of 1 by 10,000 of the diameter of a proton, but they were detected. So black holes can be detected by these invisible to our eyes gravitational waves also. So these are the waves in which black holes have been detected. So this is a picture of the LIGO detections. They were detected by gravitational waves. The waveforms are shown, the chirp waveform with the inspiral, merger, and ring down. And at the bottom is shown a heat map showing the intensity versus frequency map of the signal which is shown above. And you can determine the masses of these objects, the merging objects, using LIGO. And what is seen that black holes come with masses which are above 5 solar masses. Neutron stars come with masses which are below around something like 2.2 solar masses or so, which is the Oppenheimer-Volkoff limit. But now, in one of the recent LIGO detections, two neutron stars have merged and given an object which lies in that in-between region, between 2.2 and 5, which is called the stellar graveyard. This is the stellar graveyard. They become neutron stars, black holes, etc. It's a graveyard. But nobody was detected till now with masses between 2.2 and 5 solar masses. And we don't know the physics of that system. So there is a big excitement about, is there some new physics going to come out from that detection? So you see, astronomical detections have brought us black holes, brought in observational proof for black holes, direct proof for black holes. So here is the M87 supermassive black hole pictured again, and the picture of the black hole at its center. The glowing thing is the accretion disk. Gravity always pulls everything towards the center. Normal gravitating bodies will be very hot at the center, again due to the Virial theorem we talked about, kinetic energy plus potential energy. So in the center, you expect a lot of heat. The binding energy which has been released, half is converted to heat. So kinetic energy plus potential energy balance is seen there. High temperatures are expected. You expect it to be glowing extremely bright, instead of which there is darkness at the center, which is the black hole. And why you have something coming on top is gravity can bend even light rays. So the portion of the accretion disk, which is behind the black hole, when we are looking at the black hole, the light radiated by the portion behind the black hole is also bent and brought forward, and we are seeing what is behind the black hole also. That is why there is a ring shape. The front portion is glowing very bright. The portion brought up from behind by the gravitational field, pulled and brought towards us, is dimmer. So this is a picture of the Milky Way galaxy. You see lots of gas clouds, lots of stars. It required immense instrumentation expertise to look track the motions of individual stars around the center of the galaxy. Next slide, please. Next slide, please. This is the black hole picture I was talking about. Glowing portion is the front of the accretion disk. The dimmer portion is the back of the accretion disk, light emitted, brought up by the black hole's gravity bent towards us. The next slide. Next slide, please. This is the Milky Way center region I was talking about. Lots of gas clouds, lots of stars. Through this, millions of stars sitting there. This year's two Nobel Prize winners, they looked at the center of the galaxy to track the paths, orbits of a handful of stars. Extreme technical expertise, extreme instrumentation involving extraordinary telescopes like the Very Large Telescopes or the gravity collaboration, which took the 4 telescopes of the Keck Observatory and made an optical interferometer out of it to attain the extreme angular resolution needed to look through all this and track the motion of just a few stars. Next slide, please. Next slide, please. Yeah. Here it is, the central region through high angular resolution observation. Side is observations without using what is called adaptive optics, which takes away the effects due to the Earth's atmosphere, brings sharp objects in images. Using adaptive optics, stars will not twinkle. Twinkling will cause blur, and you can see individual those black dots, stars as black dots. And that is how you could track the orbit of S2, which was tracked, is shown on the right edge picture. And you can notice that the focus of the orbit is marked in that picture. At the one end of when you are close to the focus, when you are at periastron, the distance between the focus and the star is extreme. Can be provided by a cluster of stars which is sitting at the focus. Now, how do you know it is not a cluster of dead stars, but a black hole? That question was answered. The star periastron point so close that any stellar cluster of which would have, of course, have a size larger than that of a black hole, from general relativity. Because if it has a biggish size, there is a quadrupole moment to the distribution of matter, and the fact that the matter is highly distributed, there will be tidal effects, etc., and the orbit would have been different. So the closed full orbit solved and the focus found, giving you the distance between the focus and the star at closest approach, proved that whatever is sitting there has to be a black hole. Yeah, it is almost 15 to year orbit around the next slide, please. Next slide, please. It talked about Doppler shifts. Oh, I think previous slide, previous. It's almost over, but previous slide, then the previous to that. Told that there is Doppler effect. Now, this is a picture showing the star S2 approaching the focus and moving away from the focus. You can see that as the star is coming towards the focus, it is becoming redder and redder. That is again another clue. It is providing you another clue to track whether it is a black hole or not, etc. Not black hole. You can see that the star is becoming redder. It is a sign of what is called a gravitational redshift. When the light is moving out of a gravitational field, it will be redshifted. When moving into a gravitational field, it will be blue shifted. That phenomenon was also noticed in the observations of these Nobel Prize winners. Next slide, please. So scientists at work. The 2017 Nobel Prize was also for the gravitational wave detection, black hole related. 2020 prize is also black hole related. So one of the black hole physics is becoming one of the more exciting parts of physics, because new physics is coming out from there with observational proofs, and great amount of theoretical work is going on in quantum gravity and quantum information in relation to black holes, which might be the next breakthrough in physics. Next slide, please. I have shown 3 images here. The first one is of a star. The second one is of a quasar. The third one I am saying is of a black hole. I will leave that to you. Is there a question you want to ask me there? I will stop here. The third one also I am telling is the picture of a black hole. Over to you. Look at the picture there. Yeah. Maybe I'll answer the question myself. Go to the next slide, please.
Teacher, next.
Yeah, next slide, please. Yeah, so this is something which everybody will ask questions about. Nothing can come out of the black hole, but you have this phenomenon called Hawking radiation, which Hawking solved for by looking at quantum field theory in a curved space-time, close to a black hole. So if a particle antiparticle pair is created, one of the particles can go into the black hole beyond the trapped surface into the event horizon, and the other can escape, carried into a rotating black hole. It has to be a rotating black hole, carrying away some of the energy of the black hole. But look at the expression for the temperature. You can see the equation, right? So you can calculate. See, if it is a 1 solar mass black hole, its temperature is 6 into 10 to the minus 8 Kelvin. And you saw the Planck radiation law, right? You can see where the energy spectrum of the radiation which is emitted will peak. And a black hole to be as bright as the sun, how much mass should it have? It should have the mass of a whole galaxy. 10 to the 11 solar mass black hole can look as bright as this. Sorry, not like that. The other way around. If you want it to be that much bright, it should have a mass of 10 to the, how much should it have? 10 to the minus 8, 10 to the 3, 10 to the minus 5 solar mass. So a black hole of mass, no, not even minus 5, right? Calculate. You tell me the answer. If you want a black hole to look as bright as the sun due to Hawking radiation, what should be the temperature of the mass of the black hole? That is the question you have to answer. So that's it. Over to you. Hello, over to you. Hello.
Yes, ma'am.
Over to you. Over.
Okay,
Go
ma'am.
to the next slide.
Oh,
I just left this formula there, that's all.
okay, ma'am. There are few questions from the chat box.
Yeah.
First is from Ashwin Amrutaraj. Is the jets from the black holes are harmful like solar flares?
See, these are enormous distances away from us. So, millions of light years and more. So, they don't directly affect us. Glowing ball of gas. Now, hot gas means high pressure gas. Outside atmosphere, outside pressure is practically zero of interstellar space. So, all stars, from all stars, this hot gas is blowing outward as a wind. In the case of the sun, it is called the solar wind. The solar wind, it accelerates outward. When it reaches the earth, for example, its speed is 400 kilometers per second. So the Earth's atmosphere, Mars has lost its atmosphere for two reasons. One is its mass is not sufficient to hold on to its atmosphere, and the temperature of the atmosphere is decided by the amount of heat energy received from the sun. Whether it is hangs on to the body is determined by the mass of the body. So Mars's mass is not enough to hang on to its atmosphere. Plus, solar wind is ablating its atmosphere, blowing it away. So the major part is because its mass is not enough. Its magnetic field from sun's ultraviolet, hard ultraviolet by the ozone layer, protected from the solar wind by the magnetic field. We are sitting very nicely. At the same time, we are at sufficient distance so that we get enough energy for all the life processes which are going on Earth. Plus, we have lots of oxygen. So we are a really unusual planet. That is why any astronomer will tell you, be careful with the planet. Don't think you can play with it. So explaining gravitational microlensing, it said in Einstein's general theory of relativity, light can be bent by a gravitational field. You must have heard about the famous experiment by Eddington, where he took pictures of the eclipsed sun to show that images of those stars which are close to the sun at that time were actually shifted in position compared to their relative positions when the sun was not in that region. So similarly, now if you have in the sky, everything is projected in the sky. So all the light, suppose you consider light which is coming from a faraway object, it's passing through a globular cluster, for example, and coming. Globular clusters have a high concentration of up to the 10 to the 5 stars. Now, if these stars are moving around, of course, so that their stability is due to random motions of the stars. So if a star moves across our line of sight, the light coming from the star will be momentarily focused. So it will suddenly blip, it will brighten up suddenly and move away. That phenomenon is called microlensing. So the star is acting, the gravitational field of the star is acting like a lens, focusing the light rays coming from the object behind. That is called microlensing. You have macrolensing by clusters of galaxies creating images, multiple images of galaxies which are far back in time and distance from us in the universe. That is gravitational microlensing. Thus, isolated black holes are existing. They can exist, right? If a single star is massive enough, at the end of its lifetime, it can collapse and become an isolated black hole. Can you reframe the question, ma'am? Is the question. I don't know what that means. Oh, somebody has solved these things. 10 to the 9, 10 to the 11. 10 to the 11 is correct. If you multiply 10 to the minus 8 with 10 to the 11, but I asked you for what is the mass, correct? The mass was sitting in the denominator. Remember that. Okay. The mass. Look at the equation and answer. What is the mass of a black hole which is shining as bright as the sun? Any other answers? I'm seeing only 10 to the 11 here. The m is sitting in the denominator. So, which black hole can shine as bright as the sun by Hawking radiation? So, the answers are wrong, what you have given. 10 to the 11, 10 to the 9, 10 to the 11, wrong. The m there is sitting in the denominator. Ten raised to 41, wrong. So you think about it. It's simple mathematics. The temperature should be some 5000 Kelvin. So what mass is the black hole which is shining as bright as the sun? Okay, work it out. Over. 10 to the 19, wrong again. It's simple multiplication. 10 to the minus 41, wrong. Just check that formula. It is all there.
Okay, ma'am. Thank you for the wonderful session.
Yeah, nobody has got it right. First learn multiplication. Okay. Yeah, 10 raised to minus 11. Somebody got it right at last. Yeah, it's 10 to the minus 11. So black holes will be very bright. They will radiate their energy. Their mass will decrease till they go up poof in a puff of radiation. So micro black holes can be as bright as stars, but they don't exist for a long. But it will take huge amounts of time for any black hole, normal known black hole, to come down to this kind of masses by Hawking radiation. That's all. So thank you.
Okay, can we move on?
Yeah, sure.
Okay, ma'am, thank you. That was a wonderful session. So we have moved on to the end of this webinar. I would like to welcome our student coordinator, Aromal P, for the vote of thanks.
I am really proud to do the role of providing vote of thanks today. We know the person here we have today is one of the pioneers in astronomy and astrophysics. I thank Professor K. Indulega to having here today with us on her busy schedule. Thank you, ma'am. I would like to thank our principal for giving us this opportunity, and I would like to express my sincere gratitude to the department HOD, teachers for organizing this webinar. And I also like to thank my coordinators, especially Sharan, for his technical support. And I thank all. Thank you all.
Thank you. Bye.
Okay, thank you very much. I extend my sincere gratitude to all those who have worked behind the seminar. Once again, I thank each one of you for joining us in the Switcher platform. Thank you.
Thanks. Bye.
Ma'am, thank you so much for the to enlighten our session with your great